There's this invisible force that basically powers our entire digital world. It's the magic that lets us email huge attachments, stream movies instantly, and just store everything. It's called data compression, and it all boils down to this one absolutely brilliant idea. I mean, have you ever zipped a big folder and just stared at how tiny it got? Or thought about how a whole 2-hour movie can stream right to your phone without a hitch? Well, that's the exact question we're going to tackle today by looking at the incredible algorithm that makes it all possible. So, to really get why this was such a breakthrough, we have to rewind a little bit. The core ideas started way back in the 40s, but it was really the internet boom in the 1980s that created this huge problem. See, bandwidth was super limited, storage was crazy expensive, and people were desperate for a way to make data smaller, faster, and cheaper to send around. Right, so this was a world that was seriously needing compression. And while some methods were out there, they had some pretty big real-world problems. Okay, so take a popular method back then called Huffman coding. Super clever, but it had one giant catch. You had to scan the entire file first to figure out its patterns before you could even start compressing it. This is where the Lempel-Ziv algorithm came in and just completely changed the game. It's way more efficient because it doesn't need to know anything up front. It just learns the patterns on the fly as it reads the data. So finding the patterns, the best way to really understand this whole on-the-fly thing is to just see it in action. So let's do it. Let's walk through an example together, step by step. All right, here's the string of ones and zeros we're going to compress. Now I know, to you and me, it just looks like a random mess. But trust me, hidden inside are the very patterns that the Lempel-Ziv algorithm is built to sniff out. Now, before we dive in, here is the one and only rule you need to remember. It's so simple. The algorithm just reads the data from left to right, and each time it finds the shortest possible phrase that it has never seen before. That's it. That's the whole idea. And with just that one rule, it builds an entire dictionary of patterns from scratch. Creating the codebook. So let's start building this dictionary or codebook right now just by reading our string. Okay, here we go. First up is a 0. Have we seen that before? Nope, brand new. So it becomes entry number 1 in our codebook. Next is a 1, also new. That's entry number 2. Simple enough, right? But now it gets fun. The next bit is a 0. Wait a second. We have seen that. It's at position 1. So our rule says we have to keep going to find the shortest new phrase. So we take that 0 and grab the next bit, another 0, which gives us 0, 0. Is 0, 0 new? Yes, it is. So 0, 0 is our third entry. Let's do it again. We see a 0, which we know, so we add the next bit, a 1, to get 0, 1. And yep, that's new, so it becomes entry number 4. And we just keep doing that. We just apply that same exact logic over and over. The next part of our string starts with 0, 1. Have we seen 0, 1? We sure have. It's sitting right there at position 4. So we tack on the next bit 1 to create the new phrase 0, 1, 1. That's our 5th entry. Then we see a 1, we've seen that, add the next 0, and bam, we get 1, 0, our 6th new phrase. And if we follow that one simple rule all the way to the end of our data, this is what we get, our final, complete codebook. We've managed to chop up that whole stream into 9 unique little phrases. And this is the magic part. We've created a custom dictionary that's perfectly tailored to this specific data, all without knowing a thing about it beforehand. Okay, that's great. We have a dictionary, but how does that actually make the file smaller? Well, we do it by turning each of those phrases into a simple 2-part code. First, you take everything except for that very last bit. We call that the prefix, and you find its position in the table. Then you just stick that final bit on the end. We call that the innovation bit because, it's the part that made the phrase new. Now check this out. This is where you can really see that rule in action. Let's look at position 5, the subsequence 0, 1, 1. The prefix is 0, 1. Okay, so where is 0, 1 in our table? Right there at position 4. And the innovation bit? Well, that's the last bit, which is a 1. So the code for 0, 1, 1 is simply 4, 1. See what's happening? We're replacing longer strings with these short little pointers. And for the final step, we just turn this pair into pure binary, what a computer can understand. We take the position number, like the 4 from our 4, 1 pair, and we just write it in binary. Then we literally just append the innovation bit, the 1, onto the end. So 4, 1 becomes 1, 0, 0, which is 4 in binary, plus that final 1, giving us our encoded block 1, 0, 0, 1. From theory to reality. Okay, we did it. We went through the whole process. We found the patterns, we built the codebook, and we created our new encoded binary string. So, now for the moment of truth. Did it actually work? So our original string was 20 bits long. And after all that hard work, our shiny new encoded string is 30 bits long. I can basically hear you through the screen right now. Hold on, wait a minute. The whole point was to make it smaller, and you just made it bigger. And yeah, you're 100% right. So what on earth is going on? Did we completely fail? No, not at all. And this is the absolute key to everything. Our tiny little 20-bit example was just too short and random to have any good repeating patterns to take advantage of. But the Lempel-Ziv algorithm totally shines on real-world files, things like text documents, images, code, because those files are packed with massive amounts of repetition. In the real world, the algorithm isn't just looking at 20 bits, it's looking back at maybe the last 32 kilobytes of data, finding huge repeating chunks that it can replace with one of its super efficient little pointers. And this isn't just theory. This is the exact kind of logic that powers the compression tools you use probably every single day, like the program 7-zip. Yep, every time you zip up a folder, you are unleashing the power of Lempel-Ziv. So next time you drag a huge folder into a zip file and watch it shrink down to almost nothing, you'll actually know the clever, simple logic behind that magic. It really makes you wonder, doesn't it? What other invisible algorithms are out there, quietly running behind the scenes, shaping our whole digital lives?